Hello, fellow knowledge seekers. Ernis here, ready to plunge into the fascinating world of artificial intelligence. Today, we're cracking open a paper that tackles a seriously cool problem. Can transformers, those super smart models powering things like ChatGPT, learn to predict randomness? I know, it sounds like an oxymoron, right? The paper is titled, Learning Pseudo-Random Numbers with Transformers, Permuted Congruential Generators, Curricula, and Interpretability, by Dao and Barakzai. Now, before you glaze over with jargon fatigue, let me assure you, we're going to break this down into bite-sized, digestible pieces. So, what's this paper about? Well, imagine you're teaching a computer to play a game of chance, like predicting the next card in a shuffled deck. But instead of a real deck, you're using a special kind of number generator called a Permuted Congruential Generator, or PCG for short. PCGs are like those old, school random number generators, but with a twist. They mix things up in a predictable way. Now, why would we want to do that? Excellent question. The authors argue that if transformers can learn to predict the output of these PCGs, it tells us something profound about their ability to recognize patterns, even in seemingly random data. It's like giving them a cryptographic puzzle to solve. If they can crack it, it suggests they're picking up on subtle relationships and can generalize their knowledge. The paper is structured like a well-designed experiment, almost like a recipe for understanding AI. Let's step into our memory palace. First, we enter the generator room. This room is filled with whirring gears and blinking lights, each representing a different type of PCG the researchers used. They tweaked the generators, creating variations with names like XSLRR and TLGC. Sounds like alien technology, doesn't it? Next, we move into the training ground. Imagine a dojo where the transformer models are put through their paces. The researchers fed the models sequences of numbers generated by the PCGs and challenged them to predict the next number in the sequence. It's like teaching a language, but the language is pure math. Now, here's where things get really interesting. The authors didn't just throw all the data at the models at once. Instead, they used something called curriculum learning. Think of it as gradually increasing the difficulty, like starting with simple addition before moving on to calculus. This involves strategically feeding the model easier sequences at first, then gradually introducing more complex ones. It's like teaching a kid to ride a bike. You start with training wheels before letting them loose on the Tour de France. The next stop on our tour is the scaling chamber, a vast hall filled with giant levers and dials. Here, the researchers explored how the size of the transformer models and the amount of training data affected their performance. They wanted to know, how much brainpower does it take for these models to crack the code of randomness? Finally, we arrive at the interpretation lab. This room is filled with glowing screens displaying intricate patterns and visualizations. Here, the authors delved into what the models actually learned. They used techniques like principal component analysis to understand how the models were representing the PCG sequences internally. It's like trying to understand what a dream means. So, what did they find? Well, it turns out that transformers can indeed learn to predict the output of PCGs. But it's not a walk in the park. They discovered that curriculum learning is crucial. By starting with simpler sequences and gradually increasing the complexity, they could significantly improve the model's ability to generalize. Precisely, and the authors didn't stop there. They found that the size of the model and the amount of training data also play a significant role. Fine, yeah, I guess. Look, the point is, this paper is a big deal. But wait, there's more. The authors also peeked inside the black box of the transformer models to see what they were actually learning. They found that the models were picking up on the underlying structure of the PCGs, identifying patterns and relationships that allowed them to make accurate predictions. It's like the models were developing a sense for randomness, which is kind of mind-blowing, isn't it? So, what's the big takeaway here? This research suggests that transformers have a remarkable ability to learn complex patterns, even in seemingly random data. It also highlights the importance of curriculum learning for training these models. By carefully crafting the training process, we can unlock even greater potential. What does this all mean for the future? Well, it opens up exciting possibilities for using transformers in areas like cryptography, where understanding randomness is paramount. It also gives us a deeper understanding of how these powerful models learn and generalize, which could lead to even more innovative applications down the road. So, there you have it, a whirlwind tour of learning pseudorandom numbers with transformers. I hope you found it as fascinating as I did. Until next time, keep exploring, keep questioning, and never stop chasing that spark of curiosity. Ernis, signing off.